Okay, so I got a little challenge for you guys. So the square root of 4 is equal to 2. And the reason for that is because 2 times 2 gives you 4. So basically, when you're trying to take the square root of a number, you're basically asking yourself, okay, I want to find a number that when multiplied by itself 2 times gives me the thing inside the square root symbol. So let's say if we want to find the square root of -1. Well, that's basically asking you, okay, find a number that when multiplied by itself 2 times gives you -1. And try to find a number that meets this criteria. Try and do this. If you say, okay, let me try -1, well, -1 times -1 gives you +1, right? Because two negatives cancel out. So any negative answer wouldn't work because negative negative makes a positive, and +1 isn't the same as -1, right? These two things don't match up. So this doesn't work out. But if you pick if you pick a positive number, well, a positive number times a positive number gives you another positive number, and that won't match up with the thing inside the square root, right? So how the hell, do we find two numbers, or a number that when multiplied by itself 2 times gives you -1? It seems like that's impossible. And in the real world, so there's something you can think about this as the real number world, where it's just positive and negatives, okay? So when I'm referring to kind of the real with the real world of mathematics, I'm just talking about positive and negative numbers. However, some dudes invented something known as I. And I represents, basically, you can think about it as, the imaginary number. So I is going to be equal to the square root of -1. Basically took something that was kind of impossible and made it possible. So now there's actually something known as basically the imaginary world. And it's actually pretty cool. But, in Algebra 2, you don't really need to know that much about, imaginary numbers and, a lot of the concepts there. You need to know like a couple of things. So the first thing you got to know is the powers of I. So you need to know that I to the second power is equal to -1. This is because if you have I is equal to the square root of -1, well, if you square both sides, the square root and this exponent cancels out. So you're just going to be left with -1. So I squared is equal to -1. Now, I to the third power is equal to -I. The reason for this is because I to the third power is equal to I to the second power times I to the first power. We know I to the first power is equal to the square root of -1. And, I to the second power is equal to -1. So this is going to be the same thing as -I, basically, right? The negative of the square root of -1, or -I, right? And we have I to the fourth power, which is going to be equal to 1. Because I to the fourth power is equal to I to the second power times I to the second power. When I to the second power is equal to -1, so it's just going to be -1 times -1, which is equal to 1. All right. Now let's say if I'm trying to find out what, and actually, let me do this here. So let's say if I want to find out what I to the 57 is. How can I do this? Your first step will be finding the largest multiple of 4 in 57. So basically, kind of what I mean by that is, look, so 4. So basically, what I'm trying to find is kind of the largest multiple of 4 that goes into 57. So in this case, I can break 57 up into 56 and 1, right? Because 56 plus 1 gives me 57, right? And 56 is a multiple of 4. And in fact, this is the largest multiple of 4. So this is what I mean by kind of breaking it down into like the biggest multiple of 4. I'm kind of saying, what is the biggest multiple of 4 when added to, some number gives you this 57 in this case. So in this case, I'm breaking I into I to the 56 power times I to the first power, right? Because you can still use your exponent rules for imaginary numbers, okay? You still use your exponent rules. Now, the reason why you break it up into multiples of 4 is because we know that I to the fourth is equal to 1. And it turns out that if you have any multiple of I to some multiple of 4. So let's say if you want to find out what I to the 8th is equal to, I to the 12th is equal to, well, this is all going to be equal to 1. So any multiple of 4, so I to any multiple of 4 is always going to be equal to 1. And the reason why is because, well, I to the 8, I can break this up into I to the 4th times I to the 4th. And we know I to the 4th is just going to be equal to 1. So this is the same thing as 1 times 1, which is just 1. And I use the same logic for I to the 12th. I just break this up into I to the 4th times I to the 4th times I to the 4th. And then all of this is all going to be equal to 1 because it's just 1 times 1 times 1. So whenever you have I to some multiple of 4, basically all you're doing is just multiplying by 1 over and over again. So, it's just I to the 56 is just going to be equal to 1. So you're just have 1 times I to the first power, which is just I. And there's your answer. If you have I to, let's say, the, 63rd power, how do we do this? Well, the greatest multiple of 4 that goes into 63 is going to be 60, right? And 60 and 3. And we're going to be left with 3, right? Because if we take 60 out of 63, we're just going to be left with 3, right? Notice how these two numbers add up to be 63 because we want to make our thing equal. All right, so I to the 60, and then this is going to be times I to the 3rd power. Now, I to the 60, this is I to some multiple of 4. So all of this is going to be equal to 1. So we're just going to be left with 1 times I to the 3rd power. And we know that I to the 3rd power is equal to negative I. So this is just going to be equal to negative I. So whenever you do these I to some power problems, you're always going to end up with, either I to the 1st power, I to the 2nd power, I to the 3rd power, or I to the 4th power. You're always going to end up with one of these 4 answers. Okay? So that's something important to know. Let's just do another example. So let's say if I want to find out what I to the 102 power is equal to. There's actually a shortcut way for this. So whenever you have I to, let's say, a 3-digit, exponent, so let's say I to the, 147th power, what you basically do is, this is actually going to be equal to I to the 47th power. So you only look at the first kind of 2 digits. And then you can set it equal to the I to the 147th power. So in this case, for this I to the 102 power, I just look at my first 2 digits and I say, okay, this is going to be equal to I to the, 0, 2 power, or just 2, right? If there's a 0 here, then you only need to focus on the first thing. So I to the 102 power is equal to just I to the 2nd power. And then I to the 2nd power is just equal to negative 1. Now, why does this work? Well, it's because when we have I to the, let's say, 136 power, well, we can break this up into I to the 36 power times I to the 100th power. And I to the 100th power, well, 100 is a multiple of 4. So this is all going to be equal to 1. And you only have to focus on the first 2 digits, right? The first 2 digits of your 3-digit thing. Okay, so this is the reason why this strategy works. It's because I to the 100th power is always equal to 1. So it's basically like you're taking I, but you're only focusing on the first 2 or actually, how have I been saying first 2? I meant last 2 digits. My bad if I said that before. Okay? And it actually turns out that if you have I to the 1047, I to the 10,047, 100,047, a million, well, guess what? You use the same strategy. You only look at the first 2, the 10s and the 1s digit, okay? Because 1,000, 10,000, 100,000, all of those numbers are multiples of 4. So basically, it's like you're multiplying 1 by, and then the first 2 digits, right? Using the same logic as before. So if you have, let's say, I to the 1047 power, this is going to be equal to, you only focus on the 10s and the 1s digit, so I to the 47th power. And I to the 47th power, well, now we know that we can break this up into 2 things. The biggest multiple of 4 that goes into 47 is going to be 44, and we're just going to be left with 3. So we can break this up into I to the 44th times I to the 3rd power. I to the 44th, it's a multiple of 4, so it's going to be equal to 1. I to the 3rd is equal to negative I. And so negative I is going to be my answer. Now, we can also have something known as complex numbers. complex numbers. So complex numbers are just, numbers that are written in this form, a plus bi. So for example, let's say 4 plus 5i is one example. Let's say 0 plus 5i, that's another example. Let's say 4 plus 0i, that's another example. So, complex numbers, they can be imaginary numbers. Because 0 plus 5i is just 5i by itself, right? But you can rewrite it as 0 plus 5i, therefore kind of converting it into this form, so it's considered a complex number. And so is this 4 plus 0i. This 0i is just, you can kind of just get rid of it, so it's just 4 by itself, and 4 by itself is a real number. However, you can rewrite it in this form, and it can be considered a complex number, okay? And complex numbers can also have fractions, so 3 over 2 plus, 4 over 5i, that's also another complex number. Now, when you're solving quadratic equations, we can put this thing to use. So let's say that if we have x squared, x squared plus 5x plus 10 is equal to 0. We can solve this using the quadratic formula. So it's going to be x is equal to negative b. And actually, for a little quick review of the quadratic formula, basically, this is going to be your a value, this is going to be your b value, this is going to be your c value. Remember that a quadratic equation written in standard form looks something like this. So in standard form, basically, you're going from highest exponent to lowest exponent. And you can think about this as x to the 0th power, right? So you're going from highest exponent to lowest exponent. So a is the coefficient of the x squared term, b is the coefficient of the x term, and c is the constant. Now, to solve this, quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so plugging the values in, negative 5 plus or minus the square root of 5 squared, which is 25, minus 4 times a times c. So we know a is equal to 1, so 4 times 1 is just 4, and c is equal to 10, so 4 times 10 is 40, divided by 2 times a, so 2 times 1 is just 2. Now we can simplify. X is going to be equal to negative 5 plus or minus the square root of negative 15 over 2. Let's break this up into two fractions. So we can actually break this up into negative 5 over 2 plus or minus the square root of negative 15 over 2. The reason why we can break this up into two fractions is because we share a common denominator, right? For example, if we have, 1/3 plus 2/3, we can break this up into, we can add this up into 3 over 3. But we can also take 3 over 3 and we can turn it into 1/3 plus 2/3 because they both share a common denominator. So that's kind of the strategy we're doing here. We're taking our thing, and because both of these terms have the common denominator, we can actually break it up into two different terms. Now the square root of negative 15, I can rewrite this as the square root of negative 1 times the square root of 15. As long as the things inside a radical multiply out to be this, well, it's equal. The square root of negative 1, I know that's equal to I. So I can actually rewrite this whole part right over here as I radical 15 divided by 2. All right, so basically I just get rid of this negative symbol and I just put an I in front. And it's going to be plus or minus negative 5 over 2. And actually, I can put the I in the front. That's not wrong at all. But let me actually do this, because this will make a little more sense. So instead of putting the I here, let me just put the I in the back. All right, these two things are still the same thing. Putting an I here means, you're multiplying I by this thing. If I put an I here, it's still the same thing, right? I'm multiplying I by this thing. And this is the answer. X is equal to negative 5 over 2 plus or minus the square root of 15 divided by 2 times I. And notice how it's in the form of a plus bi, right? A plus bi. And, for a plus bi form, right, this a value right over here, real number, right? This a value right over here is a real number. This b value right over here, is also a real number. but it's this I right over here that makes this bi part imaginary. Okay, so yeah, it's similar to the examples I showed before. This 4 right over here represents this a part. This b right over here represents this 5. Both of them are real numbers. However, it's this I at the end of bi. It's this I at the end of bi that makes this the imaginary part of the complex number. Okay, I probably should have said this earlier, but a complex number has a real part and an imaginary part. Okay, I was a little late, but we move on. Now, how does this look graphically? So in this case, right, actually, if I graph this function out, so if I actually graph out y is equal to x squared plus 5x plus 10, what you notice is that it never crosses the x-axis. So the x-axis right over here is down here, this dark, line, and notice how this actually never touches this line, meaning that it has imaginary solutions. Okay, so remember, right, if I have, let's say, x squared minus 1, right, the solutions for this quadratic equation, or the zeros for this quadratic equation, are x is equal to -1 and x is equal to +1, right? Because when I plug in either -1 or +1 into x, it's going to make my y value equal to 0, right? However, in the equation I did before, well, notice how my y value can't really be 0 because my function doesn't even touch 0 in the first place, right? So that's the thing. Whenever you end up with an imaginary number, you're going to have a function that does not touch the x-axis. So this is something really important. And I actually seen a question on like the Algebra 2 regions that's like, if a function has imaginary roots, what might be the possible graph for the function? And the answer would be a function that doesn't even touch the x-axis in the first place. And complex numbers, it's very, very easy to add and subtract them. This is literally the same thing as what you do with polynomials. If you want to add complex numbers, you just add the real parts together, and then you just add the imaginary parts together. So 3 plus 4i plus 5 plus 3i is equal to 8 plus 7i. Just combine like terms, right? You add all the real terms together, add all the I terms together. You get your answer. And subtracting complex numbers is the same process. If you have 4 plus 5i, and this is going to be minus, let's say, -3 plus 5i, well, what you do is, first of all, you distribute the negative sign. So you're going to get 4 plus 5i, and then negative makes positive. So there's going to be plus +3, and then after that, this is going to be minus 5i. And then now you just, this is 7. 5i minus 5i is going to be 0i. You could just put nothing there. But yeah, 7 is the answer. Multiplying imaginary numbers, relatively the same. If you have 7 plus 6i times 3 minus 5i, we do, remember, DDP, double distributive property. Distribute the 7 to both terms, and then you distribute the 6i to both terms. So 7 times 3 is 21. 7 times -5i is -35i. 6i times 3 is going to be 18i. And then 6i times -5i is going to be -30i squared. Because 6 times 5 gives me, 6 times -5 gives me -30, and I times I gives me I squared. But the thing is, we know that, I don't have it in this slide, but we know that I squared is equal to -1. So I squared is equal to -1. So you're going to have -30 times -1. 2 negatives cancel out to be a positive. And 30 times 1 is just 30, so I just crossed out the 1. Now let's just combine like terms. So -35i plus 18i, that's -17i. 30 plus 21 is 51. That's our answer. And our answer is going to be 51 minus 17i. And, usually I just like to write things in a plus bi form. Let's say if I have 5 divided by 9 plus 3i, and I want to rewrite this in a plus bi form. How can I do this? The problem is that I have an I in the denominator. So, it would be nice if my I was in the numerator. If I wanted to convert this into a complex thing in the form of a plus bi, well, this would just be 5i divided by 12. right? So our imaginary part is going to be 5 over 12i, and then our real part is going to be 0, so it's going to be 0 plus 5 over 12 times I as our answer. But the problem is that, once again, you have this imaginary thing in the denominator. So what do? Well, what you have to do is you have to multiply by the complex conjugate. So in the denominator, we have a complex number in the form of a plus bi. And what we're going to do is we're going to multiply the top and the bottom of this by a minus bi. So in this case, it's going to be 9 minus 3i instead of 9 plus 3i. And this is something known as the complex conjugate. Now remember to multiply the top and the bottom, okay, to keep this thing equal. If I just multiply the bottom, then this isn't the same expression. So, or, it's gonna lead to like a completely different answer if you just multiply the bottom of this by a minus bi. Okay, so for the top, you're gonna do the distributive property. So 5 times 9 is 45, and it's gonna be minus 15i, right? Because 5 times negative 3i. And for the bottom, notice that you have a difference of 2 squares. So right over here, we have something in this form. So a plus b times a minus b, right? In this case, 9 plus 3i times 9 minus 3i. And this is just going to result in a squared minus b squared. So in this case, I can actually rewrite my denominator as a squared. So a squared is 9 squared. And it's going to be minus b squared. So b squared is, in this case, it's 3i squared, right? So this minus 3i squared. And if you're really unsure about doing it this way, well, remember, you can always do the double distributive property if you want. So you can always do the double distributive property. So 3i squared is going to be equal to, 3 squared is 9, and I squared is just going to be negative 1. Now, notice how there's 2 negatives. So negative makes a positive, right? Because in this case, we have 9 times negative 1, which is negative 9. So 3i squared is going to be negative 9, and these 2 negatives cancel out. So we're just going to be left with 45 minus 15i divided by, and then we have freaking 81 plus 9. So 81 plus 9 is 90. All right. So you can see how powerful the complex conjugate is, because what it allows you to do is it creates this difference of 2 squares. And we're able to take advantage of the fact that I squared is equal to negative 1, right? So we're basically converting this imaginary part into a real part, which, removes it completely from the denominator. So, we're just left with 45 minus 15i. And then once again, I'm just going to break this up into 2 fractions. So this is equal to 45 over 90 minus 15i over 90. 45 over 90 is 1/2. 15 over 9. All right, so this is, I can divide 90 by 5. So what's 90 divided by 5? That's going to be 9 divided by 5. That's going to be freaking, I don't even know, 18. So this is going to be 1/2 minus 3 over 18i. That's going to be our answer in a plus bi form, okay? So, whenever in like a practice problem or something, you have something like 5, or let's say you have something like 4 divided by 5 minus 3i, and then it asks you to kind of simplify this expression. Well, what it's basically asking you to do is kind of converting it into a plus bi form. So your goal is just trying to get rid of the I from the denominator. And all you have to do is just multiply the top and the bottom by the conjugate, or just the same thing except the sign is flipped, and you'll get your answer. Okay?